to recap what it means to compare two series. And just to bring back the graphs from the previous video, we have the idea that if we have a convergent series, B sub n, then anything that's smaller term by term must also converge to some smaller value. And if we have a divergent series, A sub n, then anything bigger must also diverge and in fact reach infinity quicker. And so if we look at this and we say, well, you know, what happens if A sub n is smaller than B sub n and B sub n is divergent? Or what happens in this situation if A sub n is smaller than B sub n and A sub n is convergent? So in this first scenario, if A sub n is bigger than B sub n, excuse me, I said that wrong. If A sub n is littler than B sub n and B sub n diverges, that means we would be saying everything out here diverges. Which means it doesn't say anything about what's happening beneath B sub n. Likewise, if we say A sub n is smaller than B sub n and A sub n is convergent, then everything in here converges. And if that's the case, then it's not saying anything about what happens above A sub n. So that leaves B sub n in an area where we can't draw any conclusions. Just like out here, it leaves A sub n in an area where we can't draw any conclusions. So in these two situations, the direct comparison test is inconclusive. And all that means is we need to have another test. And so we then come up with something called the limit comparison test. And what the limit comparison test says is when this is inconclusive, then what we can do is we can still compare them. We can still compare A sub n to B sub n. But what we're going to do then is we're going to create a ratio of the two limits. And we're going to evaluate that ratio. And if we get a finite and positive value, then the two series behave in the same manner. So if we compare a convergent series to something we want to know, then they're both going to converge. If we compare a divergent series to something we need to know, then they're going to both diverge. So what the limit comparison test is saying is we can't do this direct comparison because we're shading in the wrong parts of the graph. But we can take a ratio and we can determine that that's finite and positive. And if that's finite and positive, then we just can, we know that they behave in the same manner. So the limit comparison test starts off a lot like the direct comparison test. We look at the series and we say, let's make this simpler. And we can make this simpler by eliminating the 4 in the denominator and really eliminating the 3 in the numerator. Let's just make it really simple. So we're going to compare this to 1 over the square root of n squared. And of course the square root of n squared is just 1 over n. And if you notice, we're starting at 3 here, which doesn't really matter because we're looking for convergence or divergence. So we're really looking for, you know, what's occurring over a very many terms. So what's happening at the beginning is really irrelevant. This would be important if we were trying to find a sum, but we're not trying to find a sum. And so we're going to compare it to this. It doesn't matter which one's a sub n or b sub n. We don't have to determine which one's bigger, but I'm going to talk about that a little bit anyway, just to make a point that we have to use a limit comparison. And all we have to do is take a ratio and evaluate that ratio, the limit of that ratio. But first we have to figure out what this one does, because we have to determine if we're going for convergence or divergence. So this is a p-series. We have a p equal to 1. And that is equal to 1. So we know that this diverges because it's not less than 1. It's equal to 1. This diverges because of the p-series test. Okay, so if we get a finite value when we evaluate the limit, we know that this is also going to diverge. If we get an infinite limit, it means we picked the wrong test. So let's talk about bigger and littler just for a minute here, even though we don't really need to when we're talking about the limit comparison. So what did I do here? I made the denominator littler, and I made the numerator littler. So the question is this whole thing littler? And I'm not so sure. So what I'm going to do is I'm just going to go ahead and grab my graphing calculator. And I'm going to graph I'm going to use my terms really carefully here. I'm going to graph the sequence because I just want to look at term by term what's happening. So here is 3 divided by the quantity, the square root of n squared plus 4. And the next one is 1 over n. 1 divided by n. And we'll look at these term by term. And let's just make this one bold, just so we can differentiate here. Okay, so when we graph these, and actually, well, there's the first one. There's the second one. Okay, so if we look at a window where we have an x min of 0, a y min of 0, that'll help. And I don't think we need a y max of 10. I think 2 will be fine. Okay, so there are the 2. So if we take a look at those 2. This is the first one. This is 3 over the square root of n squared plus 4. And this is 3 over, not 3, this is 1 over n. This ends up being the smaller one. This ends up being the a sub n. This ends up being the b sub n. And so really from 3 out here, we're looking at 3 out. We could use the direct comparison test because term for term we have something smaller. We know this diverges, so we know this should diverge. So we really could use the direct comparison test, okay, on this one. But we're going to use the limit comparison to show that we end up getting a finite limit. So we're going to take the limit as n goes to infinity. And it's easier to put the more complicated one on the top, just algebraically. But it really doesn't matter. But 3 over the square root of n squared plus 4 over 1 over n. So we're going to go ahead and evaluate that limit. So that's the same as saying the limit as n goes to infinity of 3 over the square root of n squared plus 4 times n. And so we're going to evaluate the limit as n goes to infinity of 3n over n squared plus 4. And that's indeterminate, so we have to do something. L'Hopital's would be okay, but I'm not really a fan of differentiating this. So I am going to use something used at the beginning of the year, and that is divide by highest power of n. And the highest power of n is n to the first power. This is the square root of n squared, that's n to the first power. So I'm going to take a limit as n goes to infinity, and I'm going to go ahead and divide this by the highest power of n. So I'm going to say 3n, I'll go to a different color here, divided by n. And so if I divide the numerator by n, I'm going to have to divide the denominator by n. And if I'm going to divide the denominator by n, then inside the radical, that's going to look like n squared. So now I divided the numerator by n and the denominator by n. I haven't changed the ratio at all, except done the same thing to the numerator as the denominator. And so the limit as n goes to infinity then, this ends up being 3. This ends up being 1 plus 4 over n squared. And so now I no longer have an indeterminate form. As n goes to infinity, this portion goes to 0. So I end up with 3 over the square root of 1, which is just 3. And so I have a finite and positive result. And so these must behave in the same way. So therefore, the series of 3 over n squared plus 4 square root also diverges by limit comparison test. For this example, we're going to look at the series 1 over n squared minus 3n minus 2, and we're going to look to compare that. And so if we look at to another series, and so if we look at this, what would be really nice is if we had something that was just kind of like 1 over n squared. That would make life really nice on us. So we're going to compare that to 1 over n squared. So let me just get rid of that. So we're going to compare it to, we're going to look at 1 over n squared. The series, as that series goes from 1 to infinity, same upper and lower limits. And so 1 over n squared looks like this right here. So that is, I'll use function notation, that's 1 over x squared. Okay, so the terms of 1 over n squared look like this. So there are the terms of 1 over n squared, and so on and so forth. And so if those are the terms of 1 over n squared, and then this function over here is the actual series. So this function is, well, I'll use a function notation again. So let's use g of x for this one. So this is 1 over x squared minus 3x minus 2. So term for term, we're talking about when, for the first term here, when n equals 1, we're way, if we would extend this up here, we're way off the grid. And even for n equals 2, we're way off the grid, and so on and so forth. We don't quite get back on the grid until maybe 1, 2, 3, the 4th term, and here's the 5th term, and here's the 6th term, and here's the 7th term, 8th term, and so on and so forth. So if we notice term for term, so term for term, so to speak, g of x, our actual series, is larger than f of x. I'm trying to be color coordinated here. And so if we know, and we do know something about 1 over x squared, in other words, if we know something about this series, and we do, this is a p series, and p is equal to 2, which is greater than 1, so we know that this series then, this series here converges because of the p-series test. So we have to do our typical test on what we're looking at here. Then if this converges, and what we're interested in here is term for term bigger, we can't really draw a conclusion. If you recall, if we have this convergent series here, we can call all of this stuff convergent. So if we can call all of that stuff convergent, what that's saying is, let me just kind of make that a little bit transparent. There we go. So if everything in here is convergent, then we're not quite sure where this line is between convergence and divergence. And so, I mean, we know it's at 1 over n, but where does that fall in here? And we could bring that out and bring that into the picture, but really what we're saying is term for term, this is bigger. We don't know if this converges as well. So the direct series test is out. The direct series test is out as a method of comparison. So we have to do the limit comparison test. So the limit comparison test says take a ratio of the two series, and I like to put the actual series in the numerator. It makes the math a little simpler. So take the limit of that ratio and determine what that limit is. And if that limit is finite and positive, then the series behave in the same fashion. So if this converges, then that converges also. If the limit is not finite and positive, then we know we've chosen the wrong test. So we're going to go ahead and take the limit as n goes to infinity of 1 over n squared minus 3n minus 2 divided by 1 over n squared. So that's the same as taking the limit as n goes to infinity of 1 over n squared minus 3n minus 2 times n squared over 1, right? Just take the reciprocal and multiply. And so if we go ahead and multiply through, we've got the limit as n goes to infinity of n squared over n squared minus 3n minus 2. And at this point, we have to evaluate this limit. We know this limit is indeterminate. We can do L'Hopital's, or we can do something that you learned at the very, very beginning of Calc AB, and that is divide by the highest power of n. And that's what I'm going to choose to do here. I'm going to divide the top by n squared and the bottom by n squared. So I am going to go ahead and say, let's multiply by 1 over n squared and 1 over n squared. That's 1, right? So we're not changing the value of the ratio at all. And so that being the case, then the limit as n goes to infinity, n squared times 1 over n squared is 1. N squared times 1 over n squared is 1, minus 3n over n squared is 3 over n. and 2 over n squared is 2 over n squared. And so we no longer have an indeterminate form. As n goes to infinity, this goes to 0, and this goes to 0, so we're left with 1 over 1. So the limit as n goes to infinity of 1 over 1 is 1. That is finite and positive. And you don't have to state that. It's common knowledge that the number 1 is both finite and positive. And therefore, 1 over n squared as n goes from 1 to infinity, and this series 1 over n squared minus 3n minus 2 as n goes from 1 to infinity behave the same. Behave in the same fashion. So the series as n goes from 1 to infinity of 1 over n squared minus 3n minus 2 also converges. Looking at this example, we have the series n plus 1 over 3n squared plus 2 as n goes from 1 to infinity. Again, looking at simplifying this, we have a power of 1 in the numerator and a power of 2 in the denominator. It would be nice to do that. N over n squared is 1 over n, so 1 over 3n would be okay. Likewise, though, we can really get rid of that 3 in front, and so we're looking at comparing this to really reducing this. We're looking at comparing it to 1 over n. So we can really make it that simple. I mean, there's a lot you can get rid of when you do a limit comparison test. That's okay. So we're going to go ahead and strip this all the way down to 1 over n. And again, we're gonna look at both of these just to be sure. We can't do a direct comparison test. But 1 over n looks like this. So we'll call that f of x. That's 1 over n. And our original series, we'll call the original one g of x. That's the n plus 1, oops, I should write that in terms of x. X plus 1 over 3x squared plus 2. I'll write that in function notation. Let me go back and write the other one in function notation as well. So that one would be 1 over x. So this original series, as we can see, the 1 over x, term for term, is out here somewhere. Okay, so term for term are out there for 1 over x. This is also a p-series. And a lot of these comparison exercises will be really simple, either p-series or geometric series, something of that fashion. P here is equal to 1, which is equal to 1. So we know that this series then is divergent because of the p-series test. We'll just call it PST. And then if it's divergent, really all we can conclude as the stuff out here is also divergent. But we want to talk about something inside here. So again, where is that transition point from divergent to convergent? We don't know. So we don't know if this also diverges or if it converges. So we're going to go ahead and look at this term by term. So term by term, we're looking at something that is smaller, term by term. And so that's what makes the limit comparison test necessary, is we're in this zone here that is inconclusive. And so we're going to go ahead then and set up the limit as n goes to infinity of the ratio of g of x over f of x. So we're going to look at n plus 1 over 3n squared plus 2 over 1 over n. And so we're going to just go ahead and algebraically rearrange this. So we're looking at n plus 1 over 3n squared plus 2 times n over 1. And as we rewrite that, we have n squared plus n over 3n squared plus 2. And I'll mix it up a little bit here. I'm going to use L'Hopital's. That's indeterminate. It's infinity over infinity, so I'll use L'Hopital's this time around. So taking the derivative gets us 2n plus 1 in the numerator, right? This derivative of n squared plus n. Derivative of this is going to be 6n. Still indeterminate, still infinity over infinity. Nice thing about L'Hopital's is you just do it as many times as you need to in order to get it into that form that is no longer indeterminate. So we take the derivative again. Derivative of 2n is 2. Derivative of 6n is 6. We no longer have an indeterminate form. We can just evaluate that directly. That's 2 over 6, or 1/3. And so 1/3 is also finite and positive. So that being the case, we can say that this series behaves in the same way as 1 over n. So that being the case, we know that the limit as n goes to infinity of n plus 1 over 3n squared plus 2, n plus 1 over 3n n squared plus 2 also diverges because of the limit comparison test. In this example, we have the series 8 over n times quantity n squared minus 1, or plus 1, excuse me. So when we look at this, we can see that if we distribute the n here, we get really an n to the 3rd power. And so we can, again, these constants here can kind of drop off. So we're going to really strip this one down, and we're just going to call that 1 over n cubed. And that's what we'll compare it to. So if we look over here, I've got the graphs, and this graph here is 1 over n cubed, so we'll call this function f of x, 1 over x cubed. And this is a function that represents our series here. So this function, we'll call that g of x, and that's 8 over x times the quantity x squared plus 1. Okay, so again, I know it's a little repetitive, but bear with me here. We're going to look at this term for term. So there's the first term, the second term, the third term, the fourth term, the fifth term, and so on. And then they get so close to the axis that they look like they rest right on the axis. And so those are the terms for 1 over n cubed. And we know if we go ahead and evaluate this, we know this falls into a p-series again. We have a p-value of 3 that's greater than 1. And so since it's greater than 1, we know that this is convergent because of the p-series test. So again, we have this convergent series that allows us to conclude something about everything that's inside of a convergent series, but it doesn't allow us to conclude anything that is outside. Again, we're looking for that transition point from something that converges to this, and we don't know where this falls in terms of that transition. So that's what makes it, again, very necessary to use the limit comparison test. So we have this actual series here that's term for term. Again, we'd have to extend this way up in order to even find the value of that first term. Maybe it's way up here somewhere, and then we would have to extend this up. Maybe the second term is about right there. third term is roughly there, fourth term. So we've got something here that term for term is larger. And when we have something that's convergent already, term for term, if something's larger, we really can't conclude anything without doing the limit comparison test. So we're going to hit that limit comparison test again. We're going to take the limit as n approaches infinity, and I'm going to again stick the existing series in the numerator, and the one I'm comparing it to in the denominator, and I'll rewrite that as a multiplication problem, 8 over n times quantity n squared plus 1 times n cubed over 1, and then simplifying it algebraically, we've got 8n cubed over, I'm going to go ahead and distribute here, n cubed plus n. And so we could do L'Hopital's. Considering we have powers of 3 here, I really don't feel like differentiating 3 times. So I'm going to go ahead and divide by the highest power of n. So I'm going to go ahead and use that approach where the highest power here is n cubed. So I'm going to divide by 1 over n cubed. I'm going to multiply by 1 over n cubed over 1 over n cubed. Again, that's just a fancy way of saying 1. So we don't change the ratio here. So 8n cubed divided by n cubed is just 8. And distributing the n cubed here, we get 1 plus 1 over n squared. And that's no longer indeterminate. So as n goes to infinity, this goes to 0, and we're left with 8 over 1. So the limit as n goes to infinity goes to 8. And no surprise here, 8 is finite and positive. So these two series behave in the same fashion. So since this converges, this original series will converge as well. So we can go ahead and say that the series as n goes from 1 to infinity of 8 over n times the quantity n squared plus 1 also converges because of the limit comparison test.